rational functions. Now, a rational function is of the form f of x equals p of x over q of x. And if you look at that form, something should peek in the back of your mind that in order to be a function here, that q of x really should not be equal to 0, right? Because if that q of x is equal to 0, we have some issues because we're not supposed to divide by 0. And herein is where we have the topic of the vertical asymptote. A vertical asymptote is set up as x equals a is a vertical asymptote of f of x if q of x equals 0 while p of x does not equal 0. So basically, if we can find those points that would make the denominator equal to 0, those will be the vertical asymptotes when it comes to graphing our graph because the function cannot equal 0 at those points. What happens with this behavior is when the graph of a rational function approaches a vertical asymptote, the function's output y moves towards positive infinity or towards negative infinity. And we're going to look at some examples of this. Okay, I'm going to go ahead and pop up all my examples on this page. Now, the first example is f of x equals 2x over x minus 3. Here, we need to look at the denominator. That's how we determine if we have a vertical asymptote. We look at the denominator. The denominator is x minus 3. We want to look at when that might equal 0. So x minus 3 equals 0. We want to solve that for x. Well, that's pretty easy. It'll be at x equals 3. What does that tell us? Well, that tells us that our vertical asymptote is the line x equals 3. This is our vertical asymptote. You're like, okay, but what does that look like? I'm going to take you over here to the TI, and we're going to graph it. Keep those for now. So I'm going to pull my TI up. I'm going to graph it. Y equals 2x divided by x minus 3. If I graph this, what we will notice here is that we have two equations, or two lines here really. Two lines, but when we get to x equals 3, they don't really cross that line. And to kind of prove that to you, what I'll do is I'll let y2 be, I can't let y2 be 3 because it's a vertical asymptote, so that's not going to work. You're just going to have to look at it, I guess. But this line here, if you were to draw a line at this x equals 3 point, you could even, sometimes it helps to do this. If you look at the table here, it says you have an error at 3. That error is your vertical asymptote. And it doesn't matter if you zoom out to try to see if it eventually crosses it. It just doesn't. So like if I zoom out a few times, you can tell that right there at that x equals 3 point, those lines don't cross it. You can trace it to make sure, and it does get really, really close to x equals 3, but it never really truly gets there. It kind of just jumps over. So I'm going to reset my zoom to a standard zoom, get a little bit better look at it. But like I said, you could trace it if you want to. It'll get close to x equals 3, but it won't ever actually touch it. It'll just wind up jumping over to the other graph at some point. And you can see it come right back down. So there's a jump at x equals 3. That is your vertical asymptote. Let's get back to the PowerPoint and solve the next couple. All right. So the next one is f of x equals 3 over x squared minus 4. So let's look at the vertical asymptote in this case. So x squared minus 4 equals 0. That's how we'll find our vertical asymptote if there is one. Well, that's x squared equals 4. If I take the square root of both sides, that's x equals plus or minus the square root of 4. Square root of 4 is 2, so this is x equals plus or minus 2. So I must have two vertical asymptotes here. I must have one at x equals 2 and one at x equals negative 2. And we can always go and look at it, right? So let's go look at this one in my slideshow. I'm not going to look at every single one of them, but let's look at this one on our TI and see how it looks. So we're looking at 3 over x squared minus 4. So y equals 3 divided by x squared minus 4. Okay, let's see what this looks like. If I graph this, oh, well, that's you could definitely see the approachment here of the vertical asymptote at -2 and at 2. Some wild looking graphs here, right? But you can clearly see where the vertical asymptotes are at. All right, back to the PowerPoint. Now you can graph the other two after we're done with them, but let's go ahead and solve them for the vertical asymptotes in these. So here, the first one we had a vertical asymptote at x equals 3. The second one, we had two vertical asymptotes. One at x equals 2 and one at x equals -2. Now let's look at the next one. Here I have f of x equals 2x minus 2 over x squared minus 1. So I need to look at when x squared minus 1 is 0. Well, if I solve that, that's x squared equals 1, which means that x has to equal plus or minus 1. So I have two vertical asymptotes on this one as well. One at x equals 1 and one at x equals -1. So those are my two vertical asymptotes for that one. And you can graph that one as well if you'd like. I'm not going to graph every single one of them. You should have a TI calculator. You should be able to graph some of these on your own. Let's look at this one. Here I have x squared plus 9 in the denominator. The overall equation is f of x equals x plus 5 over x squared plus 9. So if I set x squared plus 9 equal to 0, here I have that x squared equals -9, which means that x would have to equal plus or minus the square root of -9, which would mean that x would have to equal plus or minus 3i, which means you'd have vertical asymptotes in the imaginary, which we aren't really worried about here. Oops. So, while you can find them, we don't graph in the imaginary here. So, technically, because they're imaginary, we have no vertical asymptotes in this case. And you can graph it and see how it looks if you want to, but you have no vertical asymptotes in this case. Now we talked about vertical asymptotes, let's talk about horizontal asymptotes. Y equals b is a horizontal asymptote of f of x equals p of x over q of x if, when comparing the degrees of p of x and q of x to determine the horizontal asymptote, if the degree of p of x is less than the degree of q of x, I'll go ahead and put all these out here for you. So for the first one, when p of x is less than q of x, or the degree of p of x is less than the degree of q of x, we will have a horizontal asymptote. Oh, darn it. We will have a horizontal asymptote at y equals 0. Case like this might be where you have x squared over, or like 4x squared plus 2x plus 1 all over, say, let's see, 3x to the third power plus 5x plus 2. The degree of the numerator, the highest degree of the numerator, is smaller than the degree of the denominator. In that case, you will have a horizontal asymptote equal to y equals 0. Okay, and remember, if you're looking at your coordinate plane here, this is your y, this is your x. A horizontal asymptote at y equals 0 is just the x-axis. This would be your horizontal asymptote. Okay. Now for the second rule, when p of x equals q of x, then what you would wind up doing is you would wind up looking at the number in front of that variable with the highest degree for both. So if you had a scenario where, say, you had a 4x squared plus 3 over 2x squared minus, or let's say plus 5, you would look at the thing in front of the variable with the highest degree on both. So the highest degree is 2. Those degrees are equal, right? And what you would wind up finding is that y would equal 4 over 2, that would be your horizontal asymptote. Or in this case, y equals 2. Want it simplified. That would be your horizontal asymptote. We'll do some more examples. Now, if p of x, the degree of p of x in the numerator is greater than q of x in the denominator, you have no horizontal asymptote. So, let's look at this example. Erase this line off of here real quick. Okay. So it says, let's find the horizontal asymptote of f of x equals 2x over x minus 3. Now, if I look at this, their variable x in the numerator and the denominator have the same degree. Technically, the degree here is 1 on both of them. What this means is we have a horizontal asymptote at y equals the number that is in front of the x in the numerator and the number that is in front of the x in the denominator. Or in this case, y equals 2 over 1, which means we have a horizontal asymptote at y equals 2. Okay. Now, I am going to, let me get down here. I'm going to try to bring you to the calculator, show you what it looks like. So we're looking at 2x over x minus 3. Y equals 2x divided by x minus 3. It says we should have a horizontal asymptote, right, at y equals 2. Well, if I put in a y equals 2 here, you should see that there is a horizontal asymptote there. Horizontal asymptote is a little bit easier to check with y equals here, because I can't hardly check the vertical asymptotes with x equals because I don't have an option for that on the calculator. But here you can see, even if you zoom out, that you truly do have a horizontal asymptote here at y equals 2. This one also had that vertical asymptote at x equals 3, if you remember, but it also has a horizontal one too. All right, let's get back to the PowerPoint. Okay, I'm going to clear, oh shoot, ugh. What's going on here? Let's see if I can end this and gonna delete that off. Okay. All right, let's start this slideshow back up. Now let's look at number 2. If I look at number 2, I've got f of x equals 3 over x squared minus 4. Now, if I'm looking at my rules here, I don't even have an x in the numerator, but technically it would be the same as x to the 0 power, right? Now, that means that the numerator has a exponent on my variable that is smaller than the exponent on my denominator. Now, what that means is that I have a horizontal asymptote at y equals 0. And you can graph it and check it if you want. I actually encourage you to graph it and check it on your TI calculator. If I look at this one, it's f of x equals 2x minus 2 over x squared minus 1. We're in the same scenario. The numerator has a much smaller degree than the denominator. Here's the degree 1 versus degree 2. Therefore, we have a horizontal asymptote at y equals 0. Easy enough. Now, how about this one? Well, here I have a 6x squared minus x minus 5 over 4 minus 3x squared. These are equivalent. Remember, when they're equivalent, you have a horizontal asymptote here of y equals that number in front of both of those equivalencies. So here it would be y equals 6 over negative 3. We would need to reduce that. So here we have a horizontal asymptote at y equals negative 2. Easy enough. All right. Now it says zeros of the rational functions. X equals c is a 0 of f of x equals p of x over q of x if. So what is our definition here? So the definition would be that you would need x equal to c to be a 0 of p of x, but not a 0 of q of x. So basically what you want to have happen is you're going to find your zeros by looking at the numerator. But keep in mind, if the denominator is 0 by that same 0, you're going to have an issue because we can't have a 0 in the denominator. Okay? So what we would do is we would find the zeros of the numerator. So here where we have f of x equals 2x over x minus 3, we would just find the 0 of f of x equals 2x. And then we would just check to make sure that it doesn't turn x minus 3 into a 0 as well. Okay, so if I set x or 2x equal to 0, I would see that we have a 0 at x equals 0. And then I would come back in here and do a check step just to make sure that when I plugged in 0, that it somehow, when I substituted the 0 in for the x in the denominator as well, that it didn't make the denominator 0. So 2 times 0 is 0. 0 minus 3 is minus 3. I don't have a 0 in the denominator, so this does truly 0 out. So here my 0 is x equals 0. Let's look at the second example. So here I have 2x minus 2 in the numerator. Let's solve that so we can see what our 0 would potentially be here. Okay, so potentially it would look like 2x equals 2, so that it looks like we might have a 0 here at x equals 1. But let's plug it in, right, and see what happens. Okay, so if I plug it in, we get 2 times 0 minus 2 over 0. Sorry, I did that wrong. Hopefully you were screaming at me through your computer. We found the 0. The 0 is 1. That's what we need to plug in there. So I'm looking at 1 squared minus 1. If I go through this, 2 times 1 is 2, minus 2. 1 squared is 1, so I have minus 1. 2 minus 2 is 0. 1 minus 0 is 0. Uh-oh, we have a problem, Houston. We have a 0 in the denominator. Have a 0 in the denominator when we use x equals 1. That's bad. That means that x equals 1 cannot be a 0 of this function. Because x can't equal 1 in this function. Because technically here we would have an asymptote. Okay. Technically we'd have an asymptote. So we have no real zeros in this function. Okay. All right. So here we are going to look at sketching graphs of rational functions. In order to do so, we're going to identify our asymptotes. We're going to identify our x or y intercepts, as well as any holes we might have in those graphs, because sometimes you wind up with a hole in a graph instead of an asymptote. And then we're going to plug in appropriate values if needed to determine whether we're above or below the x-axis. The horizontal asymptote may help with this. So here we want to sketch a graph of f of x equals 2x minus 2 over x squared minus 1. Now, let's start with the vertical asymptote. For the vertical asymptote, we really need to look at the denominator, right? Take that denominator, we need to set it equal to 0. Okay, what we find out here is that x squared equals 1, which means that x equals plus or minus 1 are vertical asymptotes. So we have a vertical asymptote at x equals 1 and x equals negative 1. Now, how about our horizontal asymptotes? Now, in this case, the degree of the numerator is less than the degree of the denominator. And we should know by our horizontal asymptote rules that that means we have a horizontal asymptote at y equals 0. right, now let's see if we can remember from Math 108 how to find the x-intercepts and y-intercepts. Okay, so to find the x-intercept, we will wind up setting our y equal to 0. Okay, I'll write that here. Oh, shoot. We're going to set our y equal to 0, solve for x. Okay, so in this case, f of x is our y. So what we would wind up doing is we would put 0 for our f of x function. Oh, darn it. Computer. Between my computer acting up and my wife trying to walk in while I'm teaching y'all, this is very tough. Alright, so if we set it equal to 0, where f of x, or y in this case, equals 0, and we back solve here, what we can wind up doing is we wind up multiplying the x squared minus 1 over. We know the denominator can't be 0, so we're really just looking at the numerator equaling 0. So that really 2x minus 2 equals 0 would be our x-intercept set up here. If we solve for x through this, what we wind up seeing is that x equals 1. So it wants us to believe that we have an x-intercept at 1, 0. You can see that this might kind of be an issue because we have a vertical asymptote there. So maybe we don't have an x-intercept. How about the y-intercept though? So for this, we want to set x equal to 0 and solve for y. Okay, if I do that, then I'm looking at y equals 2 times 0 minus 2 over 0 squared minus 1, which is negative 2 over negative 1, which is just 2. So this one should be 0, 2 for our y-intercept. Maybe not such a problem right there. Now we need to get to sketching. Now, I'll go ahead and give you this hint. If you're going to sketch one out, or you're trying to work it on my math lab with a sketch, or you're even just trying to pick one out of a group that's the correct sketch, you have a TI calculator. You can use it in this class. Please use it to your advantage. Now I'm jumping over here to my calculator. I already have it typed in, my y equals, and I'm just going to do mine on a standard zoom, which is just your 10 by 10 window. Now if we look at this, we should be able to see everything we've outlined and kind of get an idea of how this does. Now we have a horizontal asymptote so that we never really touch the x-axis, so that kind of gets rid of us having that crossing point on the x-axis. But we do see our vertical asymptote here as well at the x equals negative 1. And we also see our y-intercept here at 0, 2. So what we need to do is we need to start kind of plotting these on our graph. So if I come over here, I'm going to restart this. Okay. This is clearly our x-axis. This is clearly our y-axis. So our y-intercept was at 2. So 1, 2. We know that we have a point that's going to hit there. We also know that we have a horizontal asymptote on this x-axis here at y equals 0. And we're going to have a vertical asymptote here at x equals 1 and x equals negative 1 is what it says, right? That's kind of how we found it to be. Now, if I kind of swing back and forth between this and my graph, what you can do is you can plot some points here to try to figure out what your x and y would be. But if you already have graphed your equation on your TI, then what you can do is you can look at your second table and get you a list of points. Now, of interest to me here is this x equals negative 1 and this x equals 1. Because if I go back to the graph here, at x equals negative 1, it's pretty clear to see you have a vertical asymptote. But at x equals 1 here, I'm not seeing an asymptote. Like, I'm not seeing any approach or anything. If I go back to the PowerPoint, what that would be a hole and not an asymptote. So sometimes sometimes we have a hole in an equation instead of an asymptote. So what happens is that it actually just kind of jumps that point there. Now, if you, like I said, if you need a table of values to help you sketch it out by hand, you can clearly get some here. Okay, so one of them here gives me, if I start with the graph on that left-hand side, I could plot these points -5 and -0.5, -3 and -1, -2 and -2. So let's see if we can get those plotted on our PowerPoint sketch. So get that started back up. So we need a point. I'm going to start the point at -5. So 1, 2, 3, 4, 5. It's -5 and -1/2. So there's a point here. And then we'll plot the point -3, -1, -3, -1. There's a point there. Oops, I don't know why my points disappeared. And then I need to do -2, -2. Okay. And remember that we have that vertical asymptote at x equals -1. I'm going to draw that vertical asymptote here in red as best I can. Like a red dotted line so that I don't run into it, hopefully, when I go to sketch. Okay. Now I'm going to go back to my color here. We also have a horizontal asymptote at x equals 0, so that when we go to plot this, I'm sketching it by hand, it looks something like this. And we need to plot that other side as well, right? Because there's two parts to this. So let's see if we can get back and get some points for that other piece. Okay, so back to my calculator here. I'm going to scroll and get some of those points on the positive side to graph here. So I'll probably graph the point 3, 0.5, 4.4, maybe a 7 and a 0.25, something like that. Just trying to get an idea of where to put these on the other side. Okay, so let's look at some of those points again. So I can go over here to x equals 3. So 1, 2, 3. At x equals 3, y equals 0.5, maybe about right there. At x equals 4, it was like a 0.4, not much lower. And then all the way over here at 7, it was at 0.25. If we came all the way up to like 2, I think it was 0.666 repeating, which is a little bit more up here. And keep in mind here that there was a gap in that 1, right? And we also know that we had the y-intercept here at 0, 2. We already have it plotted. So what it came to be was something that looked a little bit, but it has a hole in it right there. And that's one of the things the TI doesn't do a great job of showing is the holes on the actual graph section. But I indicated the hole by an open circle right there, because technically we do have a hole there. This is actually a hole and not a vertical asymptote. And though it may be rough, it is our sketch of our graph. Okay. Now, let's do another one. Let's see if I can erase some of this. Gonna have to get out of the slideshow real quick. Erase some of this. Now what I'm going to do for the next two examples, I'm going to let you sketch them on your own and use your TI calculator on your own to look at the sketch of them. But we are going to find all the things they ask for here. So the first thing will be the vertical asymptote. Now with the vertical asymptote here, I need to look at the x plus 4 being 0, which means we should have a vertical asymptote here at x equals -4. Okay. So x equals -4 should be our vertical asymptote. As far as horizontal asymptotes go, these variables here both have the same exponent. So because they're equal, it needs to be a a ratio of the numbers out in front of them. Technically, the numbers out in front of them are a 1 and a 1. So here, our horizontal asymptote should be y equals 1. Okay. We can find our x-intercept here by setting y equal to 0 and solving for x. If that's the case, then you're really looking at 0 equals x minus 3 over x plus 4. If you multiply the x plus 4 over to the left-hand side, it goes away. So you're really just looking at 0 equals x minus 3. So we should have an x-intercept at x equals 3, or the point 3, 0. If you're looking at a y-intercept, you want the x to be 0. So you'll let the x be equal to 0, and you will solve for y. So in this case, y should be negative 3/4. So you should have an intercept for your y at 0, negative 3/4. And from there, you should be able to use your calculator as well as these 4 bits of information to get you a pretty decent sketch of your graph. Now, I'll find the same 4 things here: vertical asymptote, horizontal asymptote, x-axis, y-axis. Okay, so the vertical asymptote. Okay, vertical asymptote here, we would need to do x squared plus 1 equals 0, and we would need to solve for x. Well, if we did that, we'd wind up with x squared equals negative 1, and we know that we can't take the square root of negative 1 and get a real number, so we have no vertical asymptote. Well, how about a horizontal asymptote? Well, if I compare my exponents here, they're the same exponent. So I should have a horizontal asymptote at y equals 2 over 1 by comparing the numbers in front of the x's squareds here. So I should have a horizontal asymptote at y equals 2. Okay, now let's see if we can find our x-intercept and our y-intercept. Okay, now my x-intercept here, like I said, I need to set y equal to 0 and solve for x. So it would be 0 equals 2x squared plus 5 over x squared plus 1. If I multiply the x squared plus 1 over, I'm going to wind up with a scenario where I'm really just trying to solve 0 equals 2x squared plus 5. If I subtract 5 over to the left-hand side, I wind up with negative 5 equals 2x squared. If I divide by 2, I get negative 5 halves equals x squared. And hopefully what you can see is I can't take the square root of a negative number, so I have no x-intercept. Okay, well, how about my y-intercept? My y-intercept will be when my x equals 0. So y equals 2 times 0 squared plus 5 over 0 squared plus 1. So looks like I have a y-intercept at y equals 5. So that would look like x equals 0 and y equals 5. So now I have my y-intercept. I don't have an x-intercept. I don't have a vertical asymptote, but I do have a horizontal asymptote. And I can use that in combination with my TI calculator to help us come up with the sketch. If you have any questions, let me know. Try your homework. Reach out to me if you need to. Other than that, I will see y'all next lecture.